about yourself. So it's going to get recorded as well. So before you, Natalie, before you walk in, we're looking at this one here, and we're saying that if we look at these three graphs here, first off, is this a function? No. Any one input of x could give you two different y values. Is this a function?
Yes.
Yeah. The one that's up there just keeps going up like so. That's also a function. And then, let's see if I can jump to it here. Then we look at this data where you have the year and the average cost. So, could you say that the average cost is a function of the year?
No. Yes.
Yes, you could, because there is one average cost per year. There's a unique cost for each year. Just like when you had the graph that was looked like this, you know, if that's cost, then this would be year. You take one cost, you get 1 year. But the graph that was like shaped like this, if you have one cost, and then you would have 2 different years. If that worked that way, then you would say no. So what do you have here? You've got one cost, 5.6, and you have 2 different years. So then that means that the years are not a function of the cost. But the cost is a function of the year. You can figure out what the cost is if you know the year. You can't figure out what year it is if you know the cost, because it could be several different years. So yeah, it's semantics, I think. Is that right? Is that the word, semantics? How things get worded in the meaning of it. So you wanted 14, 17, and 19. Oh, review. How about the rest of you? Do you have any other numbers? Same one, same one. Let me just, no new emails. I was just thinking if somebody was at home and they were asking a question, they can shoot me an email right up until class and I'll answer it. I don't know how clear that is. When we do this, oh, there we go. When we do this, then it's more clear, better. Okay, so 14 is, which of these are formulas? So, if it's a formula, that means that you're going to have an output and an input, which are variables. So in this case here, area is equal to pi r squared. What would be the input? Radius, and the output? Area. So is that a formula? Yeah. Ax plus by is equal to c. We got too many variables, don't we? Yeah, because you're not, yes, that ax plus by equals c is not a formula, but it's a form. It's a way that we can write equations. But it's not necessarily used to find an output. E equals mc squared. Energy is equal to, what is it, the mass times the speed of light squared? Is that what it is? Or is it the speed of light times, what is m? Mass. What is c? Speed of light squared equals mc squared. So that's a formula, because you can have these two inputs here and come up with E. These can be different. A minus, or x minus ax plus a is equal to x squared minus a squared. Is that a formula? Do we use that to find outputs? No. This is just rearranged a factored form of this. This is a difference of squares. That's all that it is. So 17, how many different outfits can be made from K shirts and L, or K skirts and L shirts? What did you say?
thought about it, but I didn't think about it.
Well, K times L, let's see if that makes sense. Use an example. So, let's say we have 3 skirts and 4 shirts. So if you have 3 skirts, 4 shirts, how many combinations can you have? So you have 1, 2, 3. Skirt A, B, C. Shirt 1, 2, 3, 4. So you could have A1, A2, A3, A4. And then you could do the same with B, and you could do the same with C. So how many would there be? 12. So if you have K and L, yeah, K multiplied by L, that works. So you're good with that. So if a recipe for M people requires G eggs, how many eggs will a recipe for N people require? Huh. M requires G. How many will a recipe for N require? Yeah, but we don't know what N is in terms of M. And we haven't been told how many eggs for N, which we're supposed to figure out.
Let's say if you have a recipe that says you need this much for this much, well, then you have more people than that. You would have to adjust it.
Do we know that N is more than M?
It's like in the baking cupcakes, if you want more or less, then you would change the amount of things you put in, but we need to know if we want more or less and how much.
We need to know whether it's going to be more or less and how much. We need to know a relationship there. If we go back, it's not like another one of these tells us, does it? No. So I feel like there's not enough information to answer that question the way it's written, no matter what they say in the back of the book.
Do we want to look at what it is in the back?
I don't know. I can't imagine there's enough information there.
19 says G divided by M and X. So like it's G over M
Yeah.
and then there's an N next to it.
Yeah, I missed that. So if you had, so M is the number of people, G is the number of eggs. So this is, M require G eggs. So the rate is going to be G eggs per M people. And if you multiplied that by N people, then the number of people would cancel and you'd be left with the eggs, which would be like N over M times G eggs. I missed that one. Does that make sense? So you're looking at the rate, comparing the number of people in the two different situations. You look at that comparison, that ratio, and that's going to be N over M. So if this number is bigger, then you take a larger number divided by a smaller number, so you'll have more eggs. If this is fewer people, then it will be a fraction of the eggs needed for M. Okay. So, shall we move on from there? Good. Good. So Logan, you been running into any bears on your bicycle? I saw you riding your bicycle the other day. Yesterday.
Yeah.
When I was going home, you were coming down the hill.
When we were running yesterday, we saw one.
How many?
We only saw one.
Just one, but there's 25 of you.
Yeah. The big boar was in my neighborhood last night. It tried to break into my neighbor's house and tried to break into Ed's garage. I think it broke down Davis's something, and it was all over, and I slept for probably 2 hours, cause my dad, my mom, and I were all just yelling out the windows whenever it would try and bang on someone's garage.
Why do they do that?
Because they've been rewarded once after getting in.
And they're not stupid.
Yeah, it's like a dog, when you teach it to sit and you give it a reward, it'll do it next time you ask it to sit.
Yeah.
That's what bears do.
Yep. You can't let them go once.
Well, you live right across from J&E Rentals, which is where they've all been hanging out, getting into stuff.
Yeah, they.
But those are all gone now, aren't they?
No, there's another, cause they killed the ones they thought were doing it, and then the next day it happened again.
It's
So they didn't
it's
get
the
right
big
one.
boar they think is doing it. We helped clean up my grandma's storage unit up there.
Well, they found out one of the units had salmon in it.
Yeah, it had
So that's not
fish
really
in it, the
the
cans.
bear's fault.
Yeah, it
Blew
had like
up.
old tuna cans.
Yeah. What do we expect?
Yeah. That, whoever left salmon in their thing should get fined.
That's what it is. Someone else had, one of the other ones, the small doors that got broken into, we helped clean everything up, and they had like actual garbage bags in there. Like there was rotten egg shells and like old beer bottles and just a bunch of stuff. Like I walked in there to pick up bags and I almost threw up, it smelled so bad.
Yeah, can't expect much else then. Hey, function notations, let's do this. Let's just take simple linear equation. Y equals 2x plus 7. So this is written as an equation. Been doing that for a long time. If you graph it, what is the graph going to look like? What will the line have for its shape and such? It's going to be a line just heading up. It's going to be something like this. And it's going to have a y-intercept of 7 and a slope of 2. So if I look at that, could we say that it is a function? Yeah, because you have one output for every input, passes the vertical line test. So then we could write it like this. And what this says is that the function of x, or f of x, is equal to 2x plus 7. So kind of like the working part of this is right here. That's the 2x plus 7. That ends up giving us an output. When we multiply x by 2, we add 7. The argument is x. And then the value of the function comes from that 2x plus 7. So the value comes from this. Comes from this side. So up here, we say, well, there's the value of the equation, and this is how we get the answer. It's the same idea, but what we're doing is we're changing some of the vocabulary a little bit. This function would have a name called f. So we could write it g of x, k of x, L of x. It could be all kinds of things. And we saw that in Algebra 1. Remember, there was like L of x was a straight line, and then there was c of x, which was a constant. It was a horizontal line. And then we had e of x, which was an exponential growth. When we were looking at 3 different scenarios for population, that was something that we did like a year and a half ago or something, or a year ago. No, a year and a half, maybe a little bit more, 2 years ago. Okay, we can write this another way. This is function notation right here. We can also write the same function f. And what this, when we do this, when we use the colon, this ends up being what we call mapping notation. You saw a little bit of this somewhere in geometry. So in this case, we say that the function f maps x onto 2x plus 7. So being that 2x plus 7 gives us the output value, we're saying that there is some number of x that gives us this value for an answer. And that number maps onto here. So if, you found something out here like 10 on our graph, this x value of 10, if we look at it this way, oh, I'm sorry, I want a 10 here, f of 10 maps to 2 times 10 plus 7. So here's the x value, and then here's 2x plus 7. So that comes out to being 27. Yeah, so we could say then f of 10 maps to 27. That's one way that we could write it. The other way that we could write it is we could do this here. We could say the function, oh, I'm sorry, I'm looking at the wrong one. Go all the way up here. Let's write it again. F of x is 2x plus 7. So then in your work you could say, well, f of 10 is equal to 2 times 10 plus 7, or 27. So these have exactly the same meaning. They're just different notations, different ways of writing the same thing. If we did this work up here, you just put 10 in here, and then you'd end up with y is equal to 27. Same. Those are the different ways of looking at this. So that takes care of vocabulary. F of x notation is function notation. The argument, the value, and then mapping notation. Questions? Does it seem straightforward? Okay, it might be, it might not be. Euler came up with it. Euler came up with a lot of things, just like, remember arcs and nodes with graph theory and geometry? What I erased when you guys came in here? That was his also. So here's one. If we use this equation, or I'm sorry, this function for the first example. So they say there's a function t when it's evaluated at c that equals 1.8 c plus 32. So that's how we take Celsius and change it into Fahrenheit. So the argument is c. The value comes from 1.8 c plus 32. So if we evaluate t of 20, what we're doing is we're saying at 20C, if we do this to it, we get such and such degrees Fahrenheit. So all we have to do is substitute, which, this seems really elementary and really simple, but unfortunately the problems that they give us right away in the homework are really hard to substitute into. So what I suggest you do is that you take care to write the original function as elementary as it seems. Do it. And then substitute the value that they're giving you for your input. Once you do that, then simply follow the order of operations, but take care with that. Because the examples that they give us are real simple and straightforward, and then they go and throw all kinds of junk at us. Parentheses, exponents, and negatives underneath the radical symbol, like for the first problem. So we go from baby cakes to really complicated. So then if we keep going, and this is just like saying y equals, we don't change what we have over here. And we just do 1.8 times 20, which is 36. 36 plus 32 is 68. I'm done. Let's jump to this one here. So here's one that's written with mapping notation. Is that example 3 or 2? I think it's 2, isn't it? So here they write, the function is f, and f evaluated at x maps to the square root of the quantity 5 squared minus x squared. So if we start our work by writing down the given function, and then they want us to evaluate f of 3 and f of r minus f of 3. So to evaluate f of 3, we're going to write it as f of 3 maps to, and then just wherever x is, plug in the 3. So now we have 5 squared minus 3 squared. And then f of 3 maps to, it's 5 squared minus 3 squared is 9, gives us 16. So then, I'm just going to keep this going over here. This is straightforward. So f of 3 is going to be 4. But then, when we evaluate f of 3, is it minus? No, it's the other way around. F of r minus f of 3. We have to look at that and think of order of operations. You have to do everything in the function evaluated at r before you subtract the function evaluated at 3. So my suggestion with this one is that you do your notation as such. I'll put it up here. If I was to write f of r minus f of 3, and then we know that f of x is this, we are going to be evaluating f of x at r. So we could write the function of r, well, I'm writing it twice, I'm sorry. I would write this as the square root of 5 squared minus, instead of x, we're going to use r. So this, that portion. Then I have subtraction. And then I bring in my radicand symbol. And if I didn't know all of this already, if I didn't know that f of 3 was equal to 4, then I would write this out. Now, I already know that it's equal to 4, so I'm just going to take a quick jump all the way down, change this value to 4. And then 5 squared minus r squared. Can you simplify that at all? 25 minus r squared? Can you further simplify that?
5 minus r.
Not 5 minus r.
Not 5 minus the root of r squared.
You can't touch this. Because you have to subtract before you take the square root. The only thing that you can simplify in parts within this, the radicand symbol, is if there's multiplication. So if, for example, I had something like 25 times 100, I could simplify that and make it 5 times 10. Because this is equal to the square root of 25 multiplied by the square root of 100. We have a property for that. We have a card on the wall in the other room. But we don't have anything for this. This would have to be factored. And you can't factor this one in anything that becomes a square root. There is no square root of this, given our skills right now. And we'll never really do it. There's not going to be a point to coming up with the square root of that value. You need r first. So just be real clear with your radicand symbol where it ends, and we know that it's whatever this is, minus 4. If you wanted to be real picky about it, you could say that this is negative 4 plus, and this is actually a little bit nicer way to write your final answer if you care to take that step. It makes it very clear what it is, as opposed to that. Questions? Let's look at what the homework is. And I might even suggest that we take a look at the first couple together. These are almost like examples that are above and beyond. They're a little challenging to substitute at first. So when you're on YouTube Live, can you pause YouTube Live and then restart the same recording? Do you know? I'm wondering.
You can pause it a little jump to where it's alive.
I don't know.
It'll be live for a little.
I'm pretty sure you can do that, though.
I don't see a place where you can. I was looking, I don't see a place where you can pause it. It's like there's just an X and then you stop. Well, that's okay. If somebody's out there watching, they can be looking at those problems. So you gotta find f of root 2. And this is the function f right here. So how do you start that work? Say again?
Just write the function back.
Yeah, write the function of x. Then what would you do? Put the square root of 2 in for x. And write it over here with the function, because you're saying the function evaluated at root 2. A radicand inside of a radicand, sure. But then underneath that radicand, you just follow the order of operations and see if you can simplify it. Yeah, and just know this, if you have this anyway, that's the square root of the square root, which is the fourth root. So you remember, this right here is the same as the square root of x. So if I have the square root of the square root, that would be like having, like you could have this of this. So inside of here is x to the 1/2, and then you have x to the 1/2 again. So that's x to the 4th, which is equal to the 4th root of x. What number multiplied 4 times equals x? Don't worry about it, we're not learning that today, but yeah, you still could have this to answer your question. So what is the square root of 2 times itself? That's just 2, yeah. You take a square root, multiply it by itself, and you're back to the root. That's a property that we worked with at one time. If you think of this right here, the square root of x squared, in other words, the number multiplied by itself that equals x squared has to be x. So now if I took the square root of x squared, if I took that amount and then I squared it, that would be like taking this here, which is x, and squaring it. So that becomes x squared. So we have that number, 2, the root, is what we get for a value here. The exponent 2 and the square root cancel one another. They are inverse operations. Another way of thinking of it. So function of root 2, square root of 23. And the book says go and change it to the nearest hundredth. You know what? Leave them as radicands like that. You skip the calculator estimate. You know that this is between 4 and 5 and a lot closer to 5. And that's good enough. There will be a time where you might need to use a calculator, but don't worry about it for these problems. So the next one, number 7, is 6 multiplied by, so you should write it as it is, multiplied by the function evaluated at -1/2. So here's the function right here. So this ends up being 6 times this value right here with a -1/2 put in for x. So the 6 doesn't go in here. See what we're doing is this, you could think of this as, in fact, I'm gonna bring it down. We could think of this as 6 times the function evaluated at x. But then in the book, what they're saying is that the function is going to be evaluated at a -1/2. So look here, and what we have is 6 multiplied by, now f of x is this, because that was told to us at the beginning of the problem set. So this value, the square root of 25 minus x squared, is what they are asking us to do. Now the -1/2 gets plugged in. So what we can say is this is 6 multiplied by the square root of 25 minus -1/2 squared. Follow your order of operations and you'll come up with an answer. So you gotta be really pure with your substituting and writing. That's what I was trying to say here earlier, is to make sure that you go line by line and you're very careful to substitute exactly what needs to be substituted. And then follow the order of operations.